We are continuing the lecture on Riemann integration. This is the third part of it. And I briefly recall what we did last time. In fact, you have seen we stopped with 4 examples, and the details of which I have printed on the board for quick reference. And we have seen that we started with the function fx equal to constant, worked out an area function, computed in the conventional way, and then we linked it up with the function f. The same exercise we did for a more sophisticated function like fx equal to mx, and then later for a function which is defined on 3 different intervals in three ways, and so also finally something discontinuous or a step function. In all these cases we have computed the area function and then verified that it is actually the primitive of the f, in the sense that the function area function a differentiated will give you the original function that you started with, wherever the function a is differentiable. This is the sum of a summary of what we did last time. So what was the problem? The problem was this: given an f on some interval AB, does there exist a function capital F defined on AB such that capital F derivative is equal to the given f? This is actually an inverse problem, because given a function, at least for the case of elementary functions, we have methods of finding the derivative, and for elementary functions we have also called something antiderivative if the derivative of that function gives the given function. So that is the thing. So our problem now is to get the antiderivative in the case of far more general class of functions. And in this context we examined these 4 examples and we got a hint. What is the hint? Compute the area under the curve. That means the area enclosed between the curve, the x-axis, the ordinates in the graph of the function. Now this could be done very easily in the case of the examples we have looked at, because it involved only taking up the areas of rectangles and triangles. But that gives a hint. So if you were to deal with more general functions which are not piecewise linear, because all the 4 cases that we considered, the function is piecewise linear. Suppose you have a function which is not piecewise linear, then how do you go about doing this? For example, suppose the function fx is equal to x squared. Now in this case what happens? Let us plot the graph of the function over the interval 0 to 1. See, it is something like this. X equal to x squared. if you were to compute the area from 0 to x, you have to actually compute the area of this shaded region, which you know is not easy. Why? Because first of all, this is not a polygonal region, and we cannot use our conventional method of finding the areas of rectangles and triangles and adding this up. So this is the difficulty even when you go to the function fx equal to x squared. So how do we work this problem out in those circumstances? So this is what we have to find out. We have to devise a method. Now let us explore this. So let us start exploring this problem. So let me take out some of the things I have printed on the board, and we will draw some figures and to get some clue into what we should be doing. Now let us start with the graph of certain continuous functions defined on the interval 0, 1 or interval AB. So you have the interval AB, and this is the y-axis. We draw the graph of the function, say something like this. And what we want is the following. We want to compute the area enclosed between this is equal to y equal to f of x. This is the graph of that. A point, an arbitrary point on this is of the form x fx. So this is the shaded area that we are after. Since this is not a polygon, now it is difficult to reckon this area. So what do you do? Is it possible to bring in a polygon into this? Polygon into the study of this? You choose a few points on the curve and join them. Then you see that you get a polygon. A polygon or a piecewise linear function which lies closer to the given curve. Therefore, one of the ways in which you can approach this problem is find the area enclosed between the piecewise linear curve, the x-axis and the ordinates at A and B, and then use that to arrive at the or compute the area of the area under the given curve. Is it possible? Now, this is the question that arises. Now you see that the points we have marked on this, on the curve, actually induces a partition of the interval A into such, say A equal to x dot. This is x1, this is x2, this is x3, this is x4, this is x5. So that's a partition of the interval. Conversely, if you choose a partition on of the interval, then you can induce certain points and then work an approximation of the curve by a piecewise linear curve. So that is possible. Now we also make an observation. Suppose we introduce more points into this partition that we already start with, and then approximate using the new partition, the way in which we have done it now. You end up with a curve which is or a piecewise linear curve which is much closer to the given curve than the one that we have considered already. Let me just elaborate. Let us take a very simple scenario that you have got an interval xi minus 1. I am just taking one of the intervals that you have, possibly I, and on that the curve is something like this. Now you see that I can approximate it straight away by this line. What I do, I am going to introduce an additional point here. Let me call that, say, xi star. So corresponding to xi star, I take the point xi star f of xi star on the curve. Now I draw a polygonal line. So you can quite easily see that the area of the new linear approximation or piecewise linear approximation that you have worked out after introducing a additional point in the partition is much more closer to the original. So one way of doing this is introducing a partition of the interval and approximating the given curve by polygonal curves. But in this case, you end up with a scenario that you have considered in example 3. There, of course, if you want to calculate the area, you would need both area of the rectangles and area of the triangles coming into the picture, which complicates the scenario. But we make an approach as we did in the case in the example 4. In the example 4, what did we do? We tried to introduce what are called step functions. Let me tell you what we can do in this case. So once again, let me take up the interval xi. Suppose the curve, the given curve is something like this on the interval xi to xi minus 1 to. Now, I'll make things rigorous later, but for the time being, let me work for the function I have drawn here. Here you see that I can approximate it by the given area by a rectangle from below. What do I mean by below? This is the area that you have to compute. And what we do is, I take a lower bound of fx on the interval xi minus 1 to xi with some conditions on f. This is assured that there is this set of numbers, because I mean, at least it's good enough if you assume f is bounded. Then there exists an infimum at some point. So let the infimum now, as is clear from the curve, the infimum is attained at this particular point, and the infimum value is given by this. Therefore, let me denote this by small n. So also, I can approximate it from above by a line segment or by a straight line. What do? I choose the maximum or the supremum of the function on the interval xi to xi minus 1, as you can see here, it is attained at this particular point, and with some conditions you can assure that it happens. So let me call the maximum value at this point of the function by capital M. Or let me just write this Mi, this Mi. Okay. Therefore, I approximate this area now by the constant function. The constant function y equal to capital Mi. So I have two approximations now. One from below, one from above. What is the area enclosed by the curve y is equal to small mi? Now this is given as mi into xi minus xi minus 1. That we have calculated using the conventional geometry. Now you see that this area is less than or equal to area of F under between xi minus 1 and xi, and this is also less than or equal to the area enclosed between y is equal to capital Mi and the x-axis with ordinates taken at x equal to xi minus 1 and x equal to xi minus 1. So this is this rectangle that we are trying to come. Now as it is clear from the figure, you see that the area enclosed or the area that we are after is squeezed between two numbers, namely m into xi minus 1 and capital M in Mi into xi minus. This is something that we observe. Okay? So if we do this for a whole partition, that means the points from all the points x1, x2, etc., xn that you introduce on the interval AB, then you get the area enclosed between the curve on the interval AB will be approximated from below by a sum, and sum of terms of this kind and sum of terms of this kind. Once you understand this, then the rest is just case mathematics. So what you have is this. You have got interval A, B. Now I take a partition x0, x1, xi minus 1, xi, xn minus 1, xi. Now on this we are given a curve, something like this. I am taking the curve to be positive for the moment. I'll continue to do so until I get to some level. So what I do is this, is the following. See, between x1, x0 and x1, I take the minimum value of f on that interval, and what is the notation I am given? It is m1. So I approximate by this line segment. And then on xi minus 1 to xi, I take the minimum value of the function and call that mi. So this is m1, this is mi, and on this interval it is going to be small m. Therefore, the area enclosed, the actual area enclosed by the curve fx, so I want to call that AF, you see that AF is bounded below by the sum of the areas of these rectangles that I have shaded here. I mean, all the possible ones. There are many in between, and this is what you get. This is equal to, from I equal to 1 to n small mi xi minus. Now I go for the approximation from the top. So what do I get? I get from the top, this is approximated by capital M1, and here it is approximated by capital Mi, and here it is approximated by capital Mn. So I have a sort of step function which is equal to capital M1 on the interval late to x1 and equal to Mi on the interval xi minus 1 to xi and on the interval xn minus 1 to b it is Mn. So I have a step function, and for that step function, if I compute the area, this is what sigma I equal to 1 to n capital Mi. So you see that the area is squeezed between these two. Now we go to the next scenario. What do? I introduce additional points on this partition. That means I introduce some point between A and x1, x1 to, several points here, so that I get suppose I take a partition which is a new partition which contains all these points but some extra points, and then work out the same scenario. So what will happen? Suppose I introduce a point xi star in between here and then go for the lower approximation. Then you see that I get a far better approximation from below to the actual area enclosed that I am interested in, because this much of new area has been brought into my account. Similarly, for the new partition, let me work out the approximation from above. What is the approximation from above? Approximation from above is, now you see, I am to lose some area from the top. So what happens is the approximation I get from the top moves down closer to the actual area. So the property of this, the effect of introducing extra points is to move the lower approximation more closer to the actual area from below and bring down the upper approximation from above to the actual area. So the same inequality will prevail for the new partition also, except that the number of partitioning points will be more than what you have, so you have a corresponding sum. So let me now start making these formats. So my question the question that I ask is this: by doing this, now at least you feel that if you were to go to the limit as the interval length goes to 0, in that case what happens? You feel that the lower approximations will get closer and closer, or in the limit go to the given curve, and upper approximations go towards more closer to the given curve. So you get better approximations. Now this is roughly the idea. Then what you ask is that the limit of this will somehow give you the, as n tends to infinity, the limit of this will give you a number, and this also will give you some number. Are they going to be equal? If they are equal, then your AF being switch speeds between these two will be equal to that. If they are not equal, then you have a problem.